All right. So what we're looking at today are polygons. Now, what polygon means is a shape where the lengths of the sides are all the same, and then the angles on the inside are all the same. Probably a common one you've seen is the square. And with a square, all the sides are the same. So this could be, say, 10 feet, 10 feet, 10 feet, 10 feet. Also, all the angles on the inside, in this case, are the same. So you have 90 degrees, 90 degrees, 90 degrees, 90 degrees. And again, we're using that symbol from before that tells us we have 90 degrees. Another one that we've seen, well, we haven't seen in this class just yet, but you might have encountered it. We'll talk about it again later. The equilateral triangle. So this is a triangle with the same size sides. So this could be, say, 5 feet, 5 feet, and 5 feet. And what you'll find is this angle is 60 degrees. This angle is 60 degrees. And this angle is 60 degrees. So these are polygons. And again, the thing with the triangle, keep in mind, all the angles on the inside add up to 180. So we're going to talk about some different types of shapes. I'll mention polygons, just sort of some versions of them. Then we're going to get into triangles. Then we're going to get into four-sided shapes, what we call quadrilaterals, and different versions of those. And then we're going to take a look at perimeter. And the perimeter is just sort of the length around something, or a length along the sides of something. But we'll get to that in a bit. So first off, let's talk about polygons. So we're going to talk about different types of polygons. The first type of polygon is called a triangle. And you can think of it as tri, and starts with that prefix, or that syllable. And what you have is it means 3. So this is 3. So you can think of your equilateral triangle, something like that. And then we have the quadrilateral. And there are quadrilaterals, there are polygons. A square is a great example. And it starts with this syllable or prefix, quad, which means 4. You can think of a square. And then we start getting into things that are maybe not as common, though some that you've actually seen. Pentagon. And it starts with this prefix, or this syllable, penta, which means 5. And I'll admit my skills at drawing the pentagon are a little dubious. So, or questionable, I should say. So let me try this. If you're familiar with the Pentagon, Washington, D.C., this is the shape of the Pentagon. And I'm probably not going to get the sides all the same length, which is what a polygon is going to require. It looks roughly like that. But 1, 2, 3, 4, 5 sides, it should be all the same length. And then we have let's take a look. Hexagon. Starts with hexa. Hexa means 6. And you've seen hexagons. We see these probably every day if you go out driving. And this is your stop sign. And again, mine's probably not going to be very accurate, but all these sides should be the same length. Then we have what's a heptagon. Starts with hepta, which means 7. So there's 7 sides that are the same length. Octagon. Octa is 8. then the nonagon. Nona means 9. And then the decagon. Deca means 10. You could think like decade, 10 years. Deca is going to mean 10. And so again, for these shapes, the sides on all of these shapes, they're all going to have the same length. So this is tri will be 3 sides, quad is 4 sides, penta will be 5 sides, hexa will be 6 sides, hepta will be 7, octa is 8, nona is 9, deca is 10, and each of these sides has the same length. So this is sort of our introduction to polygons. Now we're going to get into this thing called perimeter. And so perimeters, we want to know the length all the way around the outside of these shapes, sort of along their edges. And so the way we're going to come up with perimeter is we just add up all the sides, or the lengths of all the sides, to each shape. So for triangle, we'll add this side length plus that length plus that length. For a square, you would add this plus this plus this plus that. For a hexagon, you would add this length to 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 this length, and that's going to give you the perimeter. Now there's a little shortcut you can use here so you don't have to always add, and we'll take a look at that when we get to the square, but that's for a little bit later. So we're going to talk about triangles now, and there's different triangles, and we're going to take a look at these in terms of 2 groups. We're going to look at triangles in terms of their sides, how many sides are the same length, maybe 2 are the same length, all of them are the same length, none of them are the same length. And then we're going to look at angles. Are they sort of small angles, big angles, or that perfect vertical, perfect horizontal right angle? So taking a look at these. So our first group based on sides. Well, the first one is the equilateral triangle. All 3 sides are the same length. Now in geometry, you might have seen this before, but to indicate the one side having a length, we might say, put a slash through it. If we put the same number of slashes in another side, that means these 2 sides have the same length. And since this is equilateral, all 3 sides have the same length, we're going to put a slash through there. So this is sort of a symbol or a marker for this side's length, which will be the same for this side, which will be the same for that side, because all 3 sides have the same length. So that's your equilateral triangle. So the next one, oh, not scaly. Isosceles. So with an isosceles triangle, 2 sides have the same length. So this side and this side would have the same length. This is going to have a different length from the other 2 sides. I'm going to put 2 slashes through there to symbolize that this has a different length. But equilateral, all 3 sides are the same. Isosceles, 2 sides are the same. Now we get to scaling. For a scaling triangle, all 3 sides have different lengths. So this side is different from that side, and both of those have a different lengths from that side. So you have 3 different lengths for a scaling triangle. So that's how we can think of triangles in terms of sides. Let's take a look at them in terms of angles. So first off, an acute triangle. In an acute triangle, all the sides have less than all the angles have less than 90 degrees. So to sort of review this, so let's say we have a perfectly vertical and perfectly flat angle. This is a 90-degree angle, or what's called a right angle. You can think of it as like a very uncomfortable chair. And this little box in here symbolizes 90 degrees. An acute angle has a measure less than 90 degrees. And an obtuse angle has a measure bigger than 90 degrees. So the right angle, perfectly flat, perfectly vertical. Acute angle is going to be smaller than the right angle. The obtuse angle is going to be bigger than the right angle. So when we talk about an acute triangle, here, all the angles are smaller than 90 degrees individually. So you can look at this one here. If we insert sort of a right angle here, we would do that. So this is smaller than 90. If you look at this, and it's a little bit smaller than 90. And then this, the 90-degree angle on there, it's still smaller than 90. So that's an acute triangle. Now obtuse. So with an obtuse triangle, there's one angle in this triangle that's bigger than 90 degrees. This is an obtuse angle. And that's going to be it right there. So that's what an obtuse angle is. So that's your obtuse triangle. Finally, we have a right triangle. And a right triangle contains a right angle. So that's going to be your right triangle. So those are your different versions of triangles. Oh, and if you're just logging on, just make sure your cameras are turned off and your microphones are turned off. And that's going to be it. But unless you have a question, switch them on, ask your question. All right. So those are the types of triangles. So now we're going to look at the types of quadrilaterals. And we're going to look at all types of quadrilaterals. We're going to get some quadrilaterals with different lengths of sides. And there's sort of a tree branch to this, or a branching out, if you will. So I'll try to squeeze this in. But first off, we're going to look at general quadrilaterals. So this is going to be any, let's see, just a little better. Any four-sided shape we're going to call a quadrilateral. I'm not going to be looking at quite the square just yet, but we're going to look at a very generic idea. And this is going to branch off. So any four-sided shape, quadrilateral. Doesn't matter how long the sides are, I'm not concerned about the angles. Four sides makes you a quadrilateral. Next, the trapezoid. So in the trapezoid, we could have sides that are all different lengths. So this one, these are different. So 4 different lengths. That's fine. The key thing with the trapezoid is this. There are 2 parallel lines. So this and this are parallel. Now remember what parallel is. It's like train tracks. They just run. Well, think of train tracks that don't curve. It's a pair of lines that never cross, but they also really maintain the same distance between them. So if this is a yard between these two, it'll always be a yard. Never more, never less. So a trapezoid has these 2 parallel lines. Now, then we get to what's called an isosceles trapezoid. So again, with this one, you could have 4 different lengths on this trapezoid. Now, here's the thing with the isosceles trapezoid. We still have these 2 parallel lines. Those have to be in there in our trapezoids. But though this side and this side are different lengths, these 2 are the same length. So you think kind of like the isosceles triangle, where the isosceles triangle has 2 sides that are the same length. Same with the isosceles trapezoid. You have 2 sides that are the same length. So quadrilaterals will lead the trapezoids. And really the difference, quadrilateral, again, any 4-sided shape, doesn't matter about angles or lengths or parallel or anything like that. And then you get to the trapezoid where again we have 4 different lengths here. Different, but we insist that 2 of these sides are parallel. In the isosceles trapezoid, we still have the parallel lines, but now we insist that 2 of the sides have the same length. So we're kind of tightening up a little bit. We're kind of adding some properties or qualifications to this quadrilateral as we move down. Now let's take a look at something else. So parallelogram. Now, with this one, we actually have 2 sets of parallel lines. These 2 lines are parallel, and these 2 are going to be parallel. So for this to work, this side and this side have to be the same length. And then this side and this side, they're also the same length. And that's going to give us 1 and 2 sets of parallel lines. Now this one here branches off. And this is what we call a rhombus. Now it's a type of parallelogram, except all four sides have the same length. So that's the rhombus. Now, what we do is we come up with something else here. It is a parallelogram. These two sides are parallel, and these two sides are parallel. The sides aren't the same length, but we do have another requirement. The angles on the insides are 90 degrees. Again, using that symbol for a 90-degree angle. Perfectly flat, perfectly vertical. So this is what we call a rectangle. And then finally what we're going to do, we're going to combine properties of the rhombus and the rectangle. Same lengths, 90-degree angles. And again, those two are parallel. These two are parallel. And this is what we call a square. So that's how we're going to take a look at our four-sided shape. We start out again with this quadrilateral. Sides could be any lengths, angles could be any measure, don't need anything to be parallel. And we can start out with this trapezoid, where we just have two parallel lines, and that's the only requirement. And then the isosceles trapezoid, two parallel lines, two sides are the same length though. Or instead of just having one set of parallel lines, like we have for trapezoids, let's go with all sides parallel. Well, that's the parallelogram, and that's what's going to develop on this side. And so we've got two sides parallel, two sides parallel. For this to work, we need these two sides to be the same length and these two sides to be the same length. And then this breaks down into what we have as a rhombus, where, okay, we can have all sides the same length, still parallel, that's parallel. So again, two sets of parallel lines. But we're not concerned about the angles. I'm not going to make them be 90 degrees or anything like that. But then we take an interest in a special type of parallelogram when the angles on the inside are 90 degrees. And those could be the same length, but these could be different lengths. And so we call that the rectangle. And then the other 90-degree parallelogram we're going to take interest in is the square, where we have the 90 degrees in each corner, and then all four sides are the same length. And so those are the four-sided shapes. Any questions about that? All right. So what I'm going to do is now move into perimeter. So perimeter, you can think of like a fence as a perimeter around something. Or you can think about this comes up in movies when someone sets up a perimeter. Like you sort of, set a perimeter on a field. And so you sort of watch the boundaries of that field. And perimeter is basically, another way of thinking about it, is a measure of the distance around a figure. So this is perimeter, the measure of distance around a figure. So we're going to talk about computing the perimeters of different shapes. So starting off with the triangle. Now, the easiest way to do this is to add up all the sides. So let's say I have a triangle like this. So to come up with the perimeter of this triangle, A plus B plus C. That's going to be the perimeter. We just add up the lengths of each side. So I'm just going to go through an example. So let's say you have a triangle like this. One side is 5 inches, one side is 7 inches, another side is 10 inches. Now all three sides are different lengths, so this is a scalene triangle. So to find the perimeter, we add up all the sides. And 5 plus 7 plus 10 is 22. And so that's going to be your answer. So for triangles, that's what we typically do. Just add up the three sides, and there you go. That's your perimeter. Now, for the rectangle, the square, the parallelogram, they're going to take a look at the circle. It's a little different. We're going to find some shortcuts, and especially for the square, because all the sides are the same length, we instead of doing where we add up four sides of the same length, we're just going to find out we can multiply by 4. So let's take a look though at the rectangle. So the idea of the rectangle is this. Again, it's a parallelogram, and these two sides are parallel, and these two sides are parallel. And it turns out when we do this, there's 90 degrees in each of the angles too. When we set up a quadrilateral this way, it means these two sides are going to be the same length and also cause these two sides to be the same length. Those 90-degree angles there. And, well, also the fact that they're parallel. They're parallel lines. So if you want to come up with the perimeter, again, we add up the sides. So length plus width plus length plus width. Now, we're going to talk more about this later. Again, this is something that's going to come up in the algebra section. But we have 2 lengths, and we have 2 widths. So that means we have 2 L's plus 2 W's. So we can use this formula to come up with the perimeter of a rectangle. And so there you go. So is this faster? Well, It's debatable if it is. Like here you got 1, 2, 3 operations. Here you got a multiplication, and an addition, still 3 operations. But this typically is the formula that you actually see. So let's go ahead and let's do a calculation. Now, oftentimes what you'll see is a rectangle where only 2 sides are labeled. So you do save a little bit of ink and effort because you don't have to label these 2 sides. We know that this side and this side are the same, and this side and this side are the same. So you could just add up the sides. 7 plus 3 plus 7 plus 3, and that would give you your answer. But let's use the formula. Now here, L is 7 miles. And the width, W, is 3 miles. So the perimeter, which is 2L plus 2W, well, this will be 2 times 7 miles plus 2 times 3 miles. We get a little more into this in algebra, but this means 2 times L, or 2 L's. That's what 2 L's means. You can do 2 times L. Multiplication is just repeated addition. So if you go L plus L plus L, if you add up 3 L's, well, that's the same as 3 times L. So we have 2 times L. So it's going to be 2 times 7 miles plus 2 times 3 miles. So you get 14 miles plus 6 miles, or 20 miles. And so that's the perimeter of that rectangle. Any questions about that? All right. So next we're going to look at is the square. And the square is going to give us some good shortcuts here for sure. So the square all 4 sides have the same length. So to come up with the perimeter, we add this side to this side to this side to this side, and that will give us the perimeter of the square. So as we do that, we're going to get this. So we have 4 S's. 1, 2, 3, 4. And so we can come up with a shortcut here as 4 times S. And so this will be the formula we're going to use for the square. So when we do examples with squares, oftentimes what will happen, they'll have to tell you it's a square first off. It can't, you want to avoid the rectangle that looks like a square, but one side's just a tiny bit shorter than the other, and that would be a problem. So they're going to tell you it's a square, at least they should. And they usually label just one side. So let me give you an example. So let's say we have a square that's 7 centimeters on each side. Well, just to save some effort and save some ink, we'll just label one of those sides. So 7 centimeters, 7 centimeters, 7 centimeters, 7 centimeters. Or if we add up the lengths of all 4 sides, 7 plus 7 plus 7 plus 7, that's going to give us our perimeter. But we could use the formula instead, and we'll get the same answer, of course. Four times S standing for side, or 4 times 7 centimeters. So 4 times 7 is 28. 28 centimeters. And that's going to be our answer. So any questions about that? All right. So another one we're going to look at, and it's the parallelogram. So the idea of the parallelogram is this. And this is the same idea that we saw before. We have 2 sets of parallel lines. These 2 are parallel, and these 2 are parallel. Now what's going to happen is that means this side and this side will be the same length. So let's call it B. And then this side and this side will also be the same length. Call it S. Now again, perimeter, we calculate it the same way. So we want to add up all the sides. The perimeter, S plus B plus S plus B. And this is going to be the same kind of formula we get for the rectangle. We have 2 S's, we have 2 B's. And so that's going to be our answer. So just like with the rectangle, we're going to use this formula here to come up with our solution, our perimeter. And again, they only need to really label one of the sides, or one side and another side, or a side in one of the sets of parallel sides, or in each of the sets of parallel sides. Where I'll show you. Okay, let's give this a unit. Yards and yards. So if we add up the sides, we can come up with the perimeter. So 20 plus 7 plus 20 plus 7, that would give us the perimeter. But let's use that formula. So 2 times 20 is 40. 2 times 7 is 14. And then we add 40 and 14, and that's going to be 54. And so that's going to be your answer. And again, they're only going to label 2 of the sides usually. So they might not, but usually that's how that goes. Any questions about that? All right. So what we do, that's it for the triangles and for the 4-sided shapes. There's one last one we talk about, and this is kind of a special one. It's called the circle. So let's say this is the center of the circle here. Now, there's some properties of circles we want to be aware of. The first one's called the diameter. And this is a distance across the circle through the center. And it's usually represented using a lowercase d. Again, this is a measure, so this is going to be, d is going to be some numerical value. So the diameter is the distance across the circle that passes through the circle center. It has a line, like this is a line here. It's not going to do something like, because you could start here, you could curve through like that. That's not a diameter. Diameter is going to be a line, so there's no curves in this shape or this distance. And goes from here to here, and it always passes through the center of the circle. So it's a line that cuts across the circle, but passes through the center. Now, the other thing is what's called a radius. And again, we represent diameter of a lowercase d. The other property is a radius. In a radius, and this is a radius here, it goes from the center of the circle to the edge of the circle. And again, it's a line. And we represent radius with the letter R. And again, it's from the center of the circle, or a line, from the center of the circle to the outside edge. So it's from the center to the circle's outside edge. And again, it's represented with an R. Now there's a special property between the radius and the diameter. It's going to be this. If you take a look at this picture, a radius, it's really any line, to be honest. It's any line from the center to the edge. Well, if you look at this, though, if you went from here to here, well, that's a radius because it goes from the center to the edge. So this part of the diameter is a radius. Likewise, if you go from this center, the same center, to this point on the edge, this is also a radius. So if we take a look, one radius, second radius. So there's two radii in a diameter. And so that's an important property of the circle. So the diameter is 2 times the radius. Or using symbols, d is 2r. Now, another formula you can get out of this, if d is 2r, well, that means the radius is half the diameter. So you'll get r equals 1/2 d. That's another formula you can get from this. We'll talk about this later in the algebra chapter, but if you divide both sides by 2, you'll get this one. All right. So when we talk about perimeters of a circle, we'll think back to the perimeters of triangles and quadrilaterals, we would just add up all the sides. The problem is a circle really doesn't have individual sides. It's this perfectly round shape. There's really no side where you see the beginning and the end. Now, how you come up with the formula for the perimeter of a circle is a bit complicated. You have to use something called the method of exhaustion. Use a technique developed by the ancient Greeks. It's in some ways similar to what people do in calculus. So I'm just going to give you the formula as it is. And the important thing to remember is that when you talk about the perimeter of a circle, we have a special term for that, the circumference. So the perimeter of a circle is the circumference. And it's the same thing. It's the distance all the way around the circle. So if you've got your circle, the circumference is this distance all the way around that circle, except you're actually on it like that. So a slightly more accurate picture. And this might be kind of hard to draw if you're doing if you're using just one pen or one pencil. But really the circumference is going to be this. So you start here, go all the way around, walking on the edge, come back to where you started. That's your circumference or your perimeter. So there's one thing I do need to mention, and there's one last special property. And with circles, this is sort of one of the sort of important characteristics. But for any circle, the following is going to be true. The circumference divided by the diameter for any circle, doesn't matter how small or how big, this is always going to be true, it's equal to this thing called pi. If you come up with a very precise measure of the circumference and a very precise measure of the diameter and divide those two, you're always going to get the same number, no matter what circle you're working with, small or large. And pi is approximately 3.14159. And I know in the text they say pi is about 3.14, and that's true. Usually you see pi written like this. In the calculations, though, they tend to use this number. So I was looking at one of the examples earlier, and I tried to come up with the answer they gave using 3.14, and I just didn't get the same answer. But if I use this number, I got the same answer the textbook got. So with pi, I'd say use this more, this longer approximation. As a fraction, it's oftentimes approximated by 22 divided by 7. Now I say approximated. Why do we have an exact measure for pi? We actually don't. It's called an irrational number. An irrational number is a number that cannot be represented as a ratio of other numbers. Now, this is a rational number, 22 divided by 7, but pi is only approximately this. It's not exactly that. A characteristic of irrational numbers is that when you represent them as decimals, they go on and on forever, and there's no pattern to the digits that show up here. They'll just seem like they're kind of random. There are actually competitions out there for memorizing the digits of pi to almost seemingly absurd lengths, like 10,000 places or something. So I don't know if it's quite 10,000. That seems incredible. It's worth a Google search. There's some pretty incredible memorization going on when it comes to pi. So there's you're also going to talk about two types of answers we get. You'll see the book talk about what are called approximate answers and exact answers. So let me do an example first. So let's say I have a circle by diameter of 10 feet. Now, pardon me, let me grab a calculator real quick here. Let's see, a scientific calculator. These kinds of calculations, the scientific calculator, for these types of calculations, a scientific calculator can help. There is a pi button on there, usually. So let's take a look at this. Now the circumference, and just like we represent perimeter with, you might have noticed this earlier, I was using a capital P. We use a capital C for circumference. Now the circumference is this formula. So this is how you find the perimeter around a circle. It's 2 pi r. So this is the perimeter or the circumference of a circle. So first off, we need this radius. 2 is a number we always put in the formula. Pi will always be in the formula. We need to come up with this. Now we're told the circle has a diameter of 10 feet. So radius is 1/2 the diameter. We need radius to find the circumference, but we've been given diameter. Well, fortunately, we plug in the 10 here, multiply by 1/2, and again, that's that formula from before. We're going to have a radius. And so that's going to be our answer. So it's going to be 5 feet. So, well, that's not our answer. I'm sorry. That's just our radius. Getting ahead of myself. So let me not box this. Let's just circle. So 5 feet. So now we have our radius. With this radius, we have a value for r. We can put it back here in that formula. So I'm going to erase this here. I'm going to do 2 versions of this. So the first version is the approximate answer. So for the approximate answer, knowing the radius is 5 feet, what we're going to do is use an approximation for pi. So this will be 2 times 3.14159. That's about pi. I mean, there's other digits here, but I'm not going to worry about them. I'm going to approximate. Times 5 feet. And if we multiply that together, well, what we'll get is 31.4159. And usually we round these answers, and typically we'll round either to the tenths or the hundredths place. I want to round to the hundredths. And if I look at the hundredths place here, I want to look at the digit to the right. It's 5 or greater. So that means this will bump up from a 1 to a 2. And these, of course, we always drop the digits behind. So that I am going to box. That is going to be my answer if it's approximate. So, and again, rounding to the hundredths place. Now, the other kind of answer you're going to get is what's called an exact answer. And the text will sometimes ask for both. With an exact answer, we don't replace pi with an approximation. We just leave pi and deal with these 2 numbers. And we just leave pi attached. So once again, circumference is 2 pi r. And we found, using that formula, that relationship between radius and diameter, r is equal to 5 feet, or half the diameter, which was 10. So what we get, 2 pi 5 feet, multiply these 2 together, we get 2 times 5 is 10. So that's where this 10 comes from. So 2 times 5 is 10, and we don't try to integrate the pi into this. We just leave it. And so that's going to be the answer. Now, the reason we call this an exact answer is we didn't try to approximate pi, so we're not approximating our answer. So what this does, this tells someone they can take any approximation they want for pi, 3.14, 3.14159, or maybe a really long approximation for pi. But the exact formula for computing this circumference will be 10 times pi. That's the exact formula for this particular circle. And we leave it up to someone else to decide how many digits they want behind the decimal for their approximation for pi. So that's going to be it. That's how we get the circumference of a circle. And again, there's 2 types of answers. You can use an approximation for pi, and that will give you an approximate answer. Or you can use pi as just a symbol, and that's going to be your exact answer. Any questions about that? So the last thing I want to mention today, it's an example. And it's one that's in the text. So let's say this. There's a tire on a bicycle with a diameter of 24 inches. So here's a question we're going to ask. If we push this bicycle forward, so the wheels rotate 8 times, well then, how far have we actually traveled? Actually, I'll just say tire. Like you take a bicycle tire, you roll it. Usually you don't. Usually attached to a bicycle. So how far does this tire travel? Let me put some more in here. I'm getting ahead of myself. So how far does this tire travel when it rolls or rotates 8 times? Now, I'm going to give you kind of a physics fact. Let's say this tire is rolling along the ground. Well, as it rolls along the ground, each point along the circumference of this tire will contact the ground. So as the tire rolls, each point on the tire contacts the ground. So you can kind of think of it like this. So we have this, here's a point, and the tire is going to be rolling like this. As it rolls, this point is going to move up the tire. So as the tire rotates, this point is going to start here, then it's going to get here, and then after one full rotation, this little point will have rotated all the way around. So the question is, how far has this tire traveled if it's done one full rotation? How far has it gone? I don't think my picture is going to be very accurate, but what the distance is going to be is this. As this does, each point on the outside of this tire contacts the ground until we get back to our original point. And so that means all the points on the outside of the tire have contacted the ground, and then finally this point contacts it again. It started here, and now it's contacted for a second time. So that means it's kind of like taking the entire circumference of the circle and just stretching it out on the ground until we get, well, back to the beginning, I guess you could say, if you could do that. So what's happening, one full rotation equals a distance of one circumference. So maybe a better way we can see it. Our tire's going to rotate. We're down here, and we've gone up to here, and now we've come all the way around. So with the red, let's see if that's really, yeah. So what the red's telling us is how much of the tire, this is the part of the tire that's touched the ground. So here it's just this one point. As this rotates, all of this has actually touched the ground. And by the time we come back to where we started, the entire circumference of the tire has contacted the ground. So for that to happen, that's kind of like taking this tire, cutting it, stretching it out, and that's going to be the distance between our starting point and our ending point. It's going to be distance of one circumference. So one rotation is one circumference. So we're dealing with 8 rotations. So this is going to be 8 of these circumferences, or 8, let's see, now C is 2 pi r. Now if we can multiply the 8 and the 2, we'll get 16. But we still need r. Now what we're told is this, in this problem, the diameter is 24 inches. And we know that to get the radius, we need to take half the diameter. Circle at this time. So radius is 12 inches. So that means 8 times the circumference was 16 pi r. We know r. So 16 pi times 12 inches. And let's see, 16 times 12. Well, 192. Let me check some arithmetic here real quick. Now, this is an exact answer. And the reason is we don't try to bring pi into the calculation. We just leave it the way it is. But if we want an approximate answer, you can put in 3.14159. And that comes out to approximately 603.1857.895 inches. And again, rounding to the hundredths place. And so this is an approximate answer. And that's going to be it. So that's going to be it for today. If you have any questions, let me know. Other than that, have a wonderful afternoon.
I have a question real quick.
Oh, yes.
It's on Thursday also? Or is it